All right, section 5-9 is on the volume of a solid by plane slicing. The objective is given a solid whose cross-sectional area varies along its length. We want to find the volume of that solid. All right, so let's take a look at another technique. This is called the washer method, and you'll see why here with our example that we're going to look at. But we're talking about a washer like nuts and bolts and washers, where a washer is kind of a flat disc, but it has a hole in the middle of it. If you can visualize that, that's the type of slice that we're going to be working with in this problem. So let's take a look at example 3. It says, let R be the region bounded by the graphs of y1 equals 6 times e to the negative 0.2x. So let's write that down. y1 is equal to 6 times e to the negative 0.2x. And it says y2 is equal to the square root of x. And then it says it's also bounded by the vertical lines x equals 1 and x equals 4. And finally, it says find the volume of the solid generated when R is rotated about the x-axis. So we're going to rotate around the x-axis. All right, so there's all the information we need. And let's start out with a sketch of this thing. So if you need your calculator to sketch it, certainly use it, but I think we can sketch this without the calculator. So let's say we've got this right here. So you've got this exponential function, which is doing something like this, and you've got a square root function, which is kind of doing something like this. And they're eventually going to intersect, but we're only worried about the region from 1 to 4, we'll say, is right here. So this is y1, this is y2. And we're rotating this thing around the x-axis, so our axis of rotation is right here. I like putting all that on the sketch there so we get the right sketch of this thing and the right rotation in there. And if you want to try to sketch what this thing looks like in 3 dimensions, go ahead and do so. I would suggest you look in the book there to see what it kind of looks like. Here's where I draw the line where I'm going to try to draw what the sketch is, because I'm not very good at sketching these in 3D. But what I do need to sketch is what the slice looks like. And so I'm going to sketch that, and that's really all you need to worry about, is what does this one slice look like. You never have to know what the whole thing looks like. I know sometimes that helps, but you don't have to have that. It's the one slice that you got to be able to sketch. Now your slice, when you sketch it in, it's perpendicular to your axis of rotation. So we've got the x-axis, that's horizontal, is our axis of rotation. That tells me my slice must be vertical. So we'll draw our slice in right here. And notice no matter where I draw that slice, it's always going to go from the y1 curve on the top to the y2 curve on the bottom. So that one slice represents all of them. Let's go ahead and name these. Now, since they've named this top curve y1 so that we don't confuse ourselves, I'm going to use that same name. So I'll call that point up there x, y1. I usually call that top point y2, but they've kind of forced my hand, I guess, a little bit on this one. So we'll call those x, y1 as the top point and x, y2 on the bottom point there. And then we're going to rotate this around the x-axis. So when we do that, when I rotate this around the x-axis, I'm going to get this little hole that's going to show up right here. And that is, oops, doesn't quite look like that. Let me try that again here. We end up with a shape that's going to kind of look like this. You'll see that here. That's the inside of it. That's the hole there, if you think about that washer again. And then the outer part of this looks like this. So you end up with this washer. Okay, again, I would refer to the book there if you want to see a better sketch of it, because I'm not very good at sketching it myself, but I at least can get a sketch in there to get an idea of what this thing looks like. All right, and so this is what we want to find the volume of. I got to find the volume of that washer. Okay. Now the way that I'm going to visualize this, or to find this volume, is I'm going to think of the the entire disk there as being just a disk, being a cylinder, and the hole that I have in the middle as being another cylinder. And by taking the difference between those two, I can get the volume of the washer. Okay, so in other words, find the volume of the whole thing, subtract out the hole in the middle, and you get the volume of the washer. So in that case, we would say that dV is equal to, we'll say pi times the big radius. I'll use capital R there to indicate the big radius of this thing. Big radius squared times height, minus pi times the little radius squared times height. So it's the difference of these two cylinders. All right, so now let's get this in terms of the points that I have labeled here. So big R, this is going to be pi times big R squared. So the big radius, if you were to measure that, the big radius goes from here to here. That right there is big R. And so that's just a vertical distance, a difference in y values. That goes from the point up there, y1, to the x-axis, which the x-axis has a y value of 0 there. So it's going to be just y1 is what big R is equal to. So it's y1. If you want to put minus 0, maybe I should put that in there just so you realize that I'm taking the difference in those y values. So it's y1 minus 0 squared times the height. Now the height, again, if I mark that on my cylinder here, you don't have to do this every time, but if it helps you to do it, then certainly put it in there. That right there is the height of this thing. We'll call that h. But if you look at your original slice there, that was the same as this thickness right here of this original slice. That's a change in x, a small change in x, so we call it dx. So our height here is dx. Now that takes care of the big cylinder. We now have to subtract out the small one, the hole that we have in the middle. So it's going to be pi times the little radius squared. So let's find what the little radius is. Again, if you come back up to your sketch here, the little radius, again, looking at that inner, that hole that we have in the middle there, that smaller cylinder, the smaller radius is this distance right here. We'll call that little r. So that's that vertical distance from y2 down to the x-axis. So that would be y2 minus 0. y2 minus 0. Again, you don't have to obviously put in the zeros there, but just so you realize we did take a difference in y values there to get that. And then finally multiply by the thickness. Now it turns out that the thickness of this entire thing is of course the same thickness here, but if you were to measure this height right here, it's the same as the height that we had over on the left side. It's the same as dx then. So this is just dx that we're going to multiply by for the height. So we end up with pi times, let's replace y1 with what it's equal to. Go back up to your curves here. y1 is actually that exponential function, 6 times e to the negative 0.2x. And we'll leave off the 0 there, so it's just 6 times e to the negative 0.2x quantity squared times dx minus pi times, take care of the second disk here, the smaller of the two. y2 now is on this square root function. So y2 is the square root of x. So it's the square root of x quantity squared. Again, I'll leave off the 0 there times dx. All right. Now you'll see there that on the right-hand side that each of those are multiplied by pi, the two terms that I have there. So I'm going to factor out the pi out front. And I'm going to factor out, you'll see that there's a dx at the end, so I'm going to factor out the dx at the end. Usually we put the differential of x at the end, so I'll put it that way. And you end up with this 6 times e to the negative 0.2x squared. Now if you want to leave it just like that, you can. I'm going to go ahead and square that. So you end up with 6 times 6, the 6 squared that is 36. And then e to the negative 0.2x, when you square that, you multiply those exponents. So this becomes e to the negative 0.4x. Again, if you just want to leave it as that whole quantity squared, you can, but that's what it looks like if we square that thing out. Now the square root of x squared, that's going to end up being just x, and we're subtracting that. All right, there's our differential equation. We are all set to do some integration. So the integral of dv is the integral of pi times 36 e to the negative 0.4x minus x dx. And we just need limits of integration there on the right side. So we want to think about this in terms of x. Our differential is x, so I need x values here. And they were actually nice enough to tell us that we're integrating this from x equals 1 to x equals 4. They told us those are the bounds. I want to take that blue slice or the green disk, whichever one you want to work with, and I want to slide it all the way over here to x equals 1 on the left and all the way over here to x equals 4 on the right. So those are my limits of integration. So I'm going to integrate from 1 to 4. All right. And you can see that this one now, they start to get a little bit more complicated in terms of the antiderivative that we'd be working with. And this is the reason why I want you to use that numerical integration. It's tough enough to get to this point. There's no reason to make this any more difficult with trying to evaluate that definite integral using fundamental theorem of calculus. So let's use our calculator. and use your fnint command here. And our function, again, was pi times 36 e raised to the negative 0.4x, and then minus x. And our variable there is x, and we're integrating this thing from 1 to 4, they said. And so we end up with a value there of 108.882, I guess. 108.882. 108.882. And they also gave us units on this problem here. They said assume that x and y are in feet, so we'd end up with cubic feet on this answer. And they also say to show your answer is reasonable, and you could do something similar to what we've done before. Draw a cylinder that encloses this whole thing, or a cone that's on the inside of it, and you know the answer's got to be somewhere in between those two. And it would at least give you an idea of how close your answer is. That is as far as we're going to go with this part of the section.